All right, so in part A of this example, all we did was we solved on the interval from 0 to 2 pi because the directions specified to do that. In part B, it specifies to find all radian solutions. However, the directions for something like this won't always explicitly state to find all solutions. They could simply write solve, put the equation, period, done. Or the directions above a bunch of examples could just say solve, period. Nothing telling you to restrict solutions between anything. So that means find all solutions, which we also call our general solutions, okay? Now, I'm just gonna pick up from here. So this will be, this video will be linked at the end of part A. I'll also have part A linked at the end of this one if you need it, but theta equals pi over 6 was one answer, and theta equals 7 pi over 6 was another answer. All right. Now here, if I just sketch a little for myself, pi over 6 is the angle that lands right about there. And if I want all radian solutions, well, then I don't only want pi over 6, which is scooped about that way. I want an angle that is coterminal to pi over 6. I want, in fact, every angle that is coterminal to pi over 6, whether I add more revolutions or if I take off some revolutions and head into the negative direction. So how big is one full revolution around the unit circle in radians? How large is that? What number do we use?
2 pi.
2 pi. So if you wrote for your part B, pi over 6 plus 2 pi, n, where n is an element in the set of integers, that's fine. And then if you did the same thing here, that's also fine. We can add a full revolution. And the fact that we're saying n is an integer, remember that includes, integers include negative numbers. And by adding a negative, you're really subtracting. So we are both going into larger angles and we're going into smaller or more negative angles, all of which, if you are adding increments or amounts, integral amounts of 2 pi, then they will all be coterminal and all overlap at that same place. But maybe you were clever and you were thinking smarter, not harder. And maybe you were clever and you were able to kind of consolidate and come up with one answer instead. What could you have done to come up with one general solution that will describe all of the answers with one answer? What could we do for that? Let's see, you want to try? Go ahead, Kate. Sorry, I wasn't making the hand raise noise. I think maybe Kate, you left your hand up.
Sorry, I had it raised from before.
Okay, guys, make sure you put it down, okay? Makai, you want to try?
Can you multiply pi over 6 and 7 pi over 6 and put them in the same one or no?
No, we don't want to multiply them. We just want to come up with a way of saying like all of these answers and all of these answers with one equation instead of saying all of the ones that land here in quadrant 1, bam, there's their equation. All the ones that land in quadrant 3 over here, so overlapping 7 pi over 6, bam, there's their equation. I want to come up with a way to basically say all of my answers in one try. Do you want to try it, Bianca?
Would you put plus pi n instead of 2 pi n?
Good. Perfect. How far apart are 7 pi over 6 and pi over 6? If we wanted to know how far apart they are, I'm just going to do this a little first. 7 pi over 6 minus pi over 6. What do you get for that answer? You can shout it out.
Pi over, or 6 pi over 6.
Yes, 6 pi over 6, which is pi. Then if I wanted to go this way again, this would be 13 pi over 6. And how far is 13 pi over 6 from 7 pi over 6? It's also 6 pi over 6. The fact that they are exactly like literally polar opposites, okay? They're polar opposites on the unit circle, complete perfect opposition to each other. They are pi apart. Because of that, instead of adding 2 pi to each of them, we can just add pi to one of them, pi n rather. It doesn't matter, and this goes for these answers as well, it doesn't matter what angle we put here or we put here, as long as we, what we put here, what we put here, as long as it lands in that space, because when you put plus 2 pi n, where n is an integer, it's gonna overlap in every direction. You'll hit everybody one way or another. It doesn't matter where you start. It's like a line, how a line has arrows on both sides. It goes on in both directions indefinitely. It doesn't matter where you start on a line. You're on the line. Are you in the middle? Are you closer to the right or the left? Who knows? It's infinite, right? So it doesn't matter which angle we use as long as it's in that spot and we add that amount. So I can go ahead. I'm just gonna, that's a little side thought process. Theta equals, I'll just use my quadrant 1 angle. I always try to use my quadrant 1 angle if possible. Pi over 6 plus pi n, comma, n is an element in the set of integers. So pi is 6 pi over 6. So if I add it once, bam, I'm at 7 pi over 6. Add it again, 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 and again. So tangent will often have a situation where adding pi will be sufficient, because the period of tangent is pi. If you think about the unit circle, it takes from here to here for tangent to repeat the pattern. So that's 0 to pi. So tangent is positive here. What sign, positive or negative, is tangent in quadrant 2? What sign? Is it positive or negative, the tangent values over here?
That's negative.
Negative.
Yeah. So here in quadrant 1, we passed all of our possible positive tangent answers. Here I pass all my negatives. Then at pi, repeat, like on the shampoo bottle, lather, rinse, repeat, right? So positive answers, negative answers, repeat again, positives, negatives. So that period repeats itself faster. So you know how like on Mercury, the day is shorter than it is on Earth because it's a fast moving planet. It orbits around the sun faster, all that, everything's faster there, right? So it's going to have a shorter day. That's one cycle of a day, or shorter year, one shorter cycle of a year, as opposed to on Earth. So tangent happens to have a shorter cycle. Whereas with sine and cosine, little side going off on a tangent, sine, what sine, S-I-G-N, is sine, S-I-N-E, in this quadrant? Come on, guys. We're honors. We're bright boys and girls over here. What sign is sine?
Positive.
Thank you. What about here?
Positive.
Yes, thank you. Here?
Negative.
Negative.
And
Negative.
negative. So sine, the period of sine, is 2 pi, the full circle going around, because if you think about the values of sine, we're at 0, 1/2, root 2 over 2, root 3 over 2, 1. Then we repeat those answers in reverse. Root 3 over 2, root 2 over 2, 1/2, 0. Then I go into those answers, but negative. Negative 1/2, negative root 2 over 2, negative root 3 over 2, negative 1. Then I do those same answers in quadrant 3 in reverse. Negative root 3 over 2, negative root 2 over 2, negative 1/2, 0. When I get here and go for that second loop, that's when sine repeats. Same idea with cosine. Same idea with secant and cosecant. The period of those is 2 pi, important, and the period of tangent and cotangent is pi. So I'm actually going to write that down. I would definitely recommend you write it down too. We'll talk about that in a second. So period of sine, cosine, cosecant, and secant is 2 pi. So you're going to make sure you have that in your notes. Write that down. I'm not writing it just for me. I'm writing it for you. And then the period of tangent, and we'll go over these definitions a little bit more in the future, but this is important now, so we'll make sure we include that. Tangent and cotangent, pi. Okay? So make sure you just kind of jot that down, write it. It helps you memorize it a little bit better. And that right there, I'll flip back in a second, was us solving part B over here, finding all solutions. So if you left it like this, you're perfectly fine. If you were able to consolidate, bravo, that's also perfectly fine, okay? And that was the other information. So if you're able to do that, you know the drill for the video, like let me know. If you need more practice with this, put a thumbs down so I know you need more. If you think you got it, put a thumbs up and I'll track it that way, okay?